Honorables, dear guests, dear colleagues, dear children, dear audience, I'm very excited today to be here with you and to see all your faces waiting for our show. I'm very proud to welcome you all on behalf of Faculty of Science at the University of Zagreb, on behalf of our more than 700 employees, almost 5,000 students, of our 7 departments, one of which is chemical department, and we are here in building of chemical department in their auditorium. And I'm very happy to welcome you all and to announce our start today. Before starting, I would like to thank Australian Embassy and as well to British Embassy for organizing this event. And of course, I would like to thank to Dr. Chrisa, who is our star, who will be the native scientist today, who will present this show for you. Thank you for coming to Faculty of Science. I hope to see you sometimes again here, maybe on our open days next April, and have fun today. Thank you.
With an interest in science, but I think Chris Smith seems to make it really fun for everyone, so thank you for coming along. Welcome to Odsjek, Strem. So thank you all for showing interest. Thank you to Dr. Jacinta Delhaize, our Australian astrophysicist, who is based here at the University of Zagreb, who came up with the idea to Dr. Smith to Croatia. He runs an extremely popular podcast. He's extremely popular in Australia, and we're so grateful that he came to Croatia to share some of his communication style with science. It's certainly exciting for all of us. I think we're all going to be in for a really good show tonight, and I'm very excited about it. Thanks also to our partners, Kemijski and Odsjek here in Croatia. So again, I won't say anything more. Thank you so much for coming. I'm really looking forward to it, and I'll get off the stage. Thanks everyone.
Jacinta Delhaize. Dolazi is Australia. Ovdje živi 3,5 godine. Sviđa mi se živjeti i raditi u Zagrebu. I had to say that because my Croatian teacher is in the audience this evening. Good evening everyone, I'm Dr. Jacinta Delhaize. I'm from Perth in Western Australia, and I currently work at Youth in Zagreb, where I have been for 3.5 years. I work here at PMF for the University of Zagreb, where I work in the field of astronomy and astrophysics. And tonight, just before I bring on Chris Smith, who you're all anxiously waiting to see, I'm going to take you on a 10-minute tour of the history of the universe. So you're going to learn about the entire history of the universe in 10 minutes. So are you concentrating? Yes, great. So as I said, I'm an astrophysicist. Who has seen Big Bang Theory? Good, lots of people. Which one is the astrophysicist? Raj, that's right, this one. Now sometimes Raj has a little bit of trouble talking to girls. Okay? But I just wanted to tell you that not all astrophysicists have trouble talking to girls. And some astrophysicists even are girls. Okay? So keep that in mind. Alright. History of the universe in 10 minutes. So, our whole universe was in a hot, dense state. When nearly 14 million years ago, expansion started. Wait, I've heard this song somewhere before. Okay, so the universe started in a very dense, small, infinitesimally small patch. And then suddenly it started to expand out very, very rapidly. And we call this inflation. In the beginning, the whole universe was something called a plasma, where you have electrons and protons, which are subatomic particles, and they were moving very, very fast. And they were trying to join together to form hydrogen atoms. But there were also things called photons, little packets of light, and they had a lot of energy, so they would hit the protons and the electrons that were trying to form hydrogen and break them apart. So the universe was this whole mess of plasma. But as it kept expanding, it kept cooling down until those packets of light didn't have enough energy to break apart the protons and the electrons. So they just started streaming off into space. And that created the very first photo that we have of the baby universe. And you can see that picture here. It's called the cosmic microwave background. So you're really looking at a baby photo of the universe here. So then the protons and the electrons, they just now join together to form hydrogen gas. So if the universe got very dark and very boring, you just had clouds of hydrogen gas floating around doing nothing. But then the universe kept expanding, kept cooling down, until gravity would start to take hold. And then you have the hydrogen clouds condensing, getting hotter and denser, until at the center, hydrogen fusion can start. And hydrogen fusion is a little baby star. So then we have the formation of stars. Some of them were small, some of them were medium-sized, just like our sun, and some of them were very, very big. And the biggest of these stars, they died in very dramatic deaths, called supernova explosions, which look something like this. They throw out their outer layers of gas, which you can see here expanding out and growing in beautiful colours. And in these supernova was forged many new elements, many of the heavy metallic elements. And what's left at the end of a supernova explosion sometimes is a very exotic object called either a neutron star or, even more exotic, a black hole. Now, if you're watching the news lately, you'll have seen that last week, there was an announcement that 2 neutron stars had collided, and this had caused the entire universe itself to shudder. It caused the release of gravitational waves, and using a LIGO detector, these have finally been detected. And when these 2 neutron stars collided, it caused a kilonova explosion, which is even bigger than a supernova explosion. And this is where metals like platinum, silver, and gold were forged. So if any of you in the audience here today are wearing a gold ring, a silver watch, a platinum ring, or have any of these metals, that came from the collision of 2 neutron stars. We know that for sure. So you are holding in your hand the result of neutron stars. Okay, so our sun is just a normal sized star, and it has some rocks and things going around it, which we call the solar system. The 8 planets plus poor little Pluto on the outside, and some other things. Okay. And then a collection of stars and big clouds of gas and dust in between is called a galaxy. So what's the name of our galaxy? The Milky Way. That's right. Okay, it's not the only galaxy out there. There are many others. Here you can see a fly-through of different galaxies. Now each photo right here is not an individual star, it's an entire galaxy containing billions of stars. And you can see, these are real pictures of galaxies. They are coming in all different shapes, sizes, colours. Some of them are close together, and some of them are further apart. And what we found is that when we look into the very, very distant universe, that over time, since galaxies were formed after the Big Bang until now, they've changed or evolved. And we call this galaxy evolution. So this is what our research team here at the University of Zagreb are working on. We study galaxy evolution. We do this using radio astronomy. This telescope that you see here is called the Very Large Array, or VLA. Astronomers are not very creative at naming their telescopes. So this is in New Mexico, in the USA, and we used it to look at this patch of sky called the cosmos field. You can see how big it is compared to the full moon. And we created a radio map of this patch of sky. And in it you can see these objects here. The red dots are our detections. This is false colour because our eyes can't see radio light, we can only see optical light. And what we can do with this data is that we can look at the stars forming inside galaxies. And we can make, the radio light actually helps us look through big dust clouds. Optical light that we see with our eyes can't travel through dust, just as we can't see through that wall. But radio light, if we had radio eyes, we would see straight through that wall. And that's what we can see. We can see more stars forming because we can look through the dust. Now there's something else we can see in the radio. Is supermassive black holes at the centers of these galaxies with stuff falling into them and getting really, really hot because of friction and releasing huge amounts of light. And in some cases, we can only see this happening in the radio. So we detected 1,000 objects that we can now see has this supermassive black hole activity happening that we didn't know was happening before. And this is going to help to revolutionize our understanding of galaxies and how they change over time. And that's it from me. So I hope you're concentrating. I hope you can understand the very brief history of the universe. So we talked all about things that are up there in space. But of course, science isn't just up there in space. Now we can turn our eyes down to the Earth, where there are a lot of interesting things happening. And this is where we're going to hear from our other expert tonight, Dr. Chrisa from the Naked Scientists. So without further ado, let's bring him on. Thank you for having me.
Do not look anywhere else. Look straight at the centre of the spiral. What I'm doing is very strongly stimulating the parts of your brain that decode movement in an inward rotating direction. What this is doing is activating nerve cells that can see movement in an inward rotating direction, and it's strongly turning off or deactivating nerve cells in an outward rotating direction. It's going to take about 15 to 20 more seconds for this to happen. And what the instruction I'm going to give you is to look away from the centre of the spiral when I count down from 10 and to look directly at my head. I'm standing in front of the white light in the middle. So let's start counting down. 10, count with me, 9, 8, 7, 6, 5, 4, 3.5, 3, 2, 1, and now look at me. Don't worry, the effect isn't permanent. So that's the only time that people look at me and go, wow. But this same illusion will work for movements in other directions as well, because your brain decodes what's happening in the world around you by using different clusters of nerve cells that break the visual world up and analyse it in terms of what it's doing. So if you look at movement in the upward direction, you can do the same thing. And if you look at a bonfire burning and watch the smoke rising, and then look at the ground, it will look to you as though the ground is imploding in on itself. Right, that's the only illusion you're going to see. The rest of what you're going to see is going to be some really serious science. Right, let's kick off with a bit of chemistry. What I've got here are some chemicals which will, when mixed together, cause a chemical reaction and produce light. Now, in the first of these tubes, I've got something which is called phenol oxalate. And this is an ester. And I've also got in the other tube some hydrogen peroxide, which is an oxidizing agent. And mixed in with the phenol oxalate is some luminol, which is the dye. Now, who knows what hydrogen peroxide is? Shout out. Bleach, yes, it's an oxidizing agent. Where do you use it? Well, it kills microorganisms, so you can sterilise things with it, can't you? So you can clean your contact lenses with it. Where else do you use it? Hair, yep, I can see you've had some of that, madam. Very nice. Yeah, okay, and where else? What about teeth whitening? You know when you look at these celebrities on telly and they've got teeth whiter than my toilet? They bleach their teeth with hydrogen peroxide, but in this case the hydrogen peroxide will react with the luminol and it will add energy to the luminol as it breaks down the phenol oxalate. The released energy fed into the luminol makes the dye become temporarily excited, and then as it becomes unexcited, it splits out the energy as photons of light. And so you should see a reaction if I mix the two together. Shall we have a go? Yeah. Okay, so if we can have the lights off, please. And you can we turn the screen down as well, possibly, Jacinta, just to get it black. Sorry about that. Okay. Can we turn that projector, just black it out or something? Can we go to a black screen on that? Just because it's very good. That's perfect, it's lovely. And can we turn the camera light off as well, please? Perfect. Right, we're all in the dark. Now, no funny business, remember it. Yes. Right, are you ready? Count me in. Three. Now it's gone to a blue thing. Can you turn that off? You'll see why I'm going to all the trouble, because it does look good. Yeah! Okay. Here we go. Count me in. 3, 2, 1. Here we go. Now, where else do you see this chemistry? And I'll tell you now, this is completely cold. It doesn't burn my hands. It's giving out no heat. Very safe. You see this in glow sticks. Yeah, glow sticks. Let's have the lights back on, please. And I will continue to do that for about another hour or so. So a very slow, nice chemical reaction. Right. Oh, thank you. Now, who can tell me what the sun is made of? There's very good answers coming out so far. Hydrogen, they're saying, Jacinta, is the astrophysicist, is that right? Hydrogen. And what else is in the sun? Bit of helium, very good. And a few other bits and pieces which are small. Yeah. How do you know that? Have you been there? So how do you know what it's made of? Someone's saying spectrum. What do you mean by that?
When you see the ray, you receive the light, when you receive the light of the sun, you can analyze which elements are made, also the temperature.
Absolutely. Good answer. Do you want to swap? You come do this. I'm just kidding, it's alright. That's the right answer. We can look at the light which comes from the sun, and written into that light is a fingerprint of the chemicals that are in the sun. Because actually the guy who invented this thing, does anyone know what this is called? Bunsen burner. Robert Bunsen was a Scotsman. He invented, apart from this thing, he invented the science of spectroscopy. And he realised that you can look at the light coming from a distant object, and you can look for the chemical fingerprint of the things that were in the thing that made the light to work out what it's made of. And the reason is that every element has atoms, and those atoms have electrons around the outside, they're negative charges, and when we give energy to atoms, the electrons absorb some of that energy, and they are temporarily kicked up to a higher energy state. They can't stay like that forever, so they have to give the energy away. And the way they give the energy away is they produce light, and because different atoms are different sizes, with different electron configurations, the amount of energy the electrons have to lose is different. So they produce different colours of light. So we can actually demonstrate that for you. I've got some spray bottles here, and I've got some salts, some different elements dissolved in alcohol. No drinking this, it's pretty poisonous. But what that means is we can give energy with this Bunsen burner to these salts, and we should be able to see what the elements are. So let me just get this a bit hotter. Can we turn the lights off, please? Okay, you can tell me what you see. Are you ready? 3, 2, 1, here comes the first one. I can make the camera guys really nervous now. Okay, what do you think that chemical is? Someone said strontium. Actually, that was my first choice of chemical to use, but we didn't have any of that, so we used lithium instead. But where do you see that chemistry being used? Fireworks. Very good. So when you're watching a nice fireworks display, that is what's happening. Right, next one. What can you see? It's a nice green colour. Yeah? There's some clever people in the audience because someone said barium. Actually, barium is what a doctor has to do to his patients when he can't curium them or helium them. But it wasn't barium, that was actually copper. But copper makes three colours. Okay, next one, here we go. And I'll put the thing out. Let me light it up again. There was some orange in there, but the main colour is not, the one you see is not orange. It's actually, look again. It's a bit subtle. Can you see it's purple? Yeah, that's actually potassium. Potassium nitrate, that one. Okay, here's the last one. You've probably eaten this, all of you. But I guarantee it. Okay, here we go. Say what you see. Yeah? It is fire. What colour? Yeah, so what salt is this? No, it's not orange juice, but that's a good thought. It's sodium. This is a salt of sodium. This is sodium chloride. And where do you find sodium chloride? Can we have the lights on, please? Sodium chloride is table salt. Yeah. So you put that on your fish and chips. Okay. Now I'm going to test you because with every bit of education, you're in the university now. We have to find out whether you learned anything. So I'm going to test you, and I'm going to ask you to use the science of spectroscopy to help me to work out what the chemical composition of one of these is. Okay, do you like gherkins? Do you like gherkins? Anyone like gherkins? Do you want to eat this? They're real. Okay. So we're going to try and work out what's in here. The way I'm going to do it is I'm going to use this piece of apparatus over here. I don't know if we can see this on the camera. This is 2 dinner forks wired up to the mains. We call this the gherkinator. This is effectively an electric chair for naughty vegetables. So what I'm going to do is to put the gherkin onto the dinner forks, making sure that it's turned off while I do it. And when I pass current through this, it will pass a very large current through the gherkin and strike an arc inside the gherkin. The arc is a spark. It will give energy to the atoms inside the gherkin, just like the Bunsen burner gave energy to the atoms inside those salts. And the dominant salt in here will give colour. We should be able to see that, and then you should be able to shout out what salt you think is in this gherkin. So if we can have the lights off, please. And all eyes on the gherkin. And count me in. 3, 2, 1. What did you see? It was orange, wasn't it? So what's in the gherkins? Well, let's have a look on the ingredients. It says there's some energy in the gherkins, and it actually says apart from gherkins in the gherkins, which is reassuring, that there is a lot of salt in the gherkins. So 1.6 hands in every 100. So very solid team, you're absolutely right. Give us lots around the floor. I couldn't do that.
You can read Croatian,
Do you want to read one? Draw one.
No, I'm alright then.
Now, the next thing I want to show you actually uses the air. Okay, so I'm going to need Jacinta's help for this. I'm sorry about the smell, by the way. That's not me, it was the gherkin. We're actually going to use air pressure. So what we've got down here is a gadget that we call a vacuum bazooka. Okay. Now the way this works is that we've got a vacuum cleaner down here. So when I turn the vacuum cleaner on, it will suck air down the tube. And this long white pipe, and by the way, anyone been in the lavatories this afternoon? You might find that your feet get wet because we borrowed some pipe work from in there. Sorry about that. But it's going to draw air down the vacuum pipe. You might have to come this way all the time. It's going to draw air down the vacuum pipe, and it's going to pull air in at this end, and it's going to pull air in at that end. What I'm going to do is put a piece of card over the end, and this means it's now only able to pull air in at that end. And we're going to put in the other end of the tube a projectile. This is made of depleted uranium. It's not really, just kidding. But I'm going to give this to Jacinta. She's going to put it in, and it's going to feel a force because the air rushing in here is going to push on the back of the projectile. It's going to go faster and faster and faster and faster down the tube until it gets to the end, and it'll be going so fast it should knock the piece of card out of the way and then fire off and hopefully shoot me up the arse because I'm going to go and stand over there. Would anyone like to volunteer to help shoot me? Who would you like?
So many good hands in the air. Alright, there's one up there. Can you come up?
That gentleman there.
Yes.
Yeah, come on there. Okay, there's your first one. There one. Right, I'm going to go stand over here in your target.
I've been waiting for this big old week.
In fact, I wonder if I can catch it in the bucket. That's the go.
Alright, so you step down this edge. Okay.
Right, if you step to roughly there, that's good. Right, there we go.
Step to this edge. Here. So you hold
On your shoulder.
On the left, move down. Okay. There you go. Now, you need to put this here. Okay. And then I turn on back and then you can let that go. Okay?
Okay, turn the vacuum on. It's a set to maximum. It's set to maximum. 1,000. There you go. Right. 3, 2, let go of the car. Let go. Take your hand off the car. That's it. Yeah. 3, 2, 1. Oh, lucky. Don't go away with that. Okay. 3, 2, 1. I think your hands are got. One more go. Best of 3. Best of 3. I've done a little bit of research and development, and I've actually come up with a refinement on the design. And what I've got here is the this one actually auto reloads, and it's also got a flat valve on here, so we don't have goes at this. Who's going to help me? There's a young lady there, very, very quick off the draw. Let's have you then. The cost of making the liquid nitrogen is actually more than the price of the 9 gallons of diesel that it takes, roughly equivalent to cremate a person at the moment. So it's probably not going to catch on right now, but maybe that's a growth industry to keep your eye on in the future. Now, I'm not going to put my hand in there, but I will put some other bits and pieces. I might put that back actually. I'm going to put some other living tissue into the liquid nitrogen. I've got some flowers here. These are not foliage flowers, real flowers. Just put that in there. What I've got now is a chrysanthemum at about -200 degrees. And instead of being nice and flexible like these chrysanthemums, this one does this. It becomes very, very fragile. Should we do it again? Yeah. So just put that in there. The liquid nitrogen takes all the energy away from the flowers. It takes a lot of the energy away from the flowers. And the polymers, the proteins that the flowers are made of, stop moving very well, so they don't bend very easily, and the water all turns to ice crystals, which makes it very brittle. Now, who knows what one of these is? Rubber glove. Who likes doing washing up? Yeah. Probably enough, no one. Why is this rubber glove stretchy? Why can I do that? What's in here? Latex, yeah. And what is latex made of?
Rubber.
Well, if I zoomed in with a really powerful microscope on this rubber glove, what I would see are long chains of molecules, like snakes or spaghetti, all writhing around. Because when things are warm, they have energy. When they have energy, particles are vibrating. So the atoms and molecules in this rubber is vibrating. And when I pull on the rubber, because they're vibrating, I can make the chains slip past each other and untangle and straighten, which is the stretch. So what will happen if I take all the energy away from the rubber glove? Well, what I now get is a rubber glove that's much less rubbery. In fact, you can do this. And then it ceases to be quite such a useful rubber glove after that. But the good thing is that once it warms up again, if I warm this back up and give it energy again from my hands, it then goes back to being rubber again. Because you have put energy back into the molecules and they begin to slide past each other once more. Right, one more little experiment. Just get up the balloon. What do you think I've got in this balloon? I've got a gas in there, yeah. And it's a gas called helium. Helium is element number 2 in the periodic table. It's a very light gas. And in fact, because the particles of helium are so small, some of them are moving really fast. In fact, if you measure them, some of them are doing 2 kilometers per second in this balloon. And because they have energy, because they're warm, they're hitting the sides of the balloon very hard and very often. And that's pushing on the side of the balloon, keeping it inflated. So what would happen if I took energy away from the helium atoms? They're going to slow down, yeah? So they're going to hit the side of the balloon less hard and less often. So what will happen to the balloon? Well, let's put the balloon in the liquid nitrogen. So the atoms of helium are losing energy to very cold liquid nitrogen. And watch what happens when I pull the balloon out, and then watch what happens as it takes energy back in from the room. Just watch what happens as the helium warms up, taking energy away from the air, and goes back up again. And actually we call that liquid nitrogen Viagra. Kids, ask your parents when you get home. One more time. Just cool that down. Shrinks it down, helium moving very slowly, picks up energy from the room, warms up the helium again, and then pretty quickly it goes again. Look like a helium balloon. You look like someone who like a helium. We've done one set of experiments with air, but I want to do another one. Who can tell me how an aeroplane flies? Well, if you're on Monarch, not very fast, is the answer. If that isn't being written timestamp, they just went past. And the Ryanair aren't flying anywhere either at the moment very often. But aeroplanes have wings, don't they? So how does a wing work? Well, a wing uses one of Newton's laws, doesn't it? For every action, there's an equal and opposite reaction. Wings are curved, and what they're effectively doing is they're pushing air downwards, so the air pushes back on the wing and lifts it up. So that's the bottom surface of the wing. It's pushing air downwards. What about the top? Well, there's another experiment we can do to show you exactly what's happening on the top of a wing. I'm going to need some volunteers. I need 3 or 4 volunteers. Let's have 4 volunteers. Okay, you'll do. Yeah, one. We need 2 boys, 2 girls. So there's ladies there. Can you do your seat out in the middle of that row? Can you get out, okay? Come on then. 2 more. There's a gentleman at the back there. Yeah, you come. And yeah, you'll do. Come on then. Right, whoop, ball's running away from me. What's your name? Eric, there you go, have a straw. And have a ball. Eric, what's your name? Adrian, have a straw, have a ball. Brilliant. You go stand next to Eric, 2 of you stand there. Face that lot if you compare it. That's it. What's your name? Green, there you go, have a straw and a ball. Very good. What's your name? Oh, there you go, straw and ball. There we go. One for you. What's your name? Lucas and a straw. Right. Now, line up in a nice straight line and face that lot. Come across this way a bit, I won't bite. So, right, what I want you to do is take your straw, right, and it's a bendy straw, so you should be able to do that. Okay, make it like that. Then, put the straw in your mouth. Don't worry, these straws haven't been used more than about 5 times. It's okay. Right, I'm going to get you to blow really hard down the straw, and then I want you to hold the ball above the end of the straw, and you should be able to get the ball to bob around above the straw. Have a go. Keep going. Keep trying. You should be able to let go of the ball. Let go of the ball. No cheating, lads. Oh, you nearly had it then. One more go. Hey, we're winner. It is possible. I'll show you how you do it. Now, what about something a bit bigger? You need a little puff to blow that one, wouldn't you? Should we try it with a hairdryer? Actually, before you go, can I borrow one of those tennis balls just briefly? Just stay there for me, let me have a minute. That one, just stay there. We've got a hairdryer, so we can have a go with the hairdryer and see if this will do it. You may not support it. There we are. Thank you. I don't think it'll do my football though. It's a little bit too heavy, I think. So I think we might need something with a bit more puff. Can I just give you that, Jacinta? So I was thinking about this, and I thought, what have I got that could actually give it a bit more welly? So I've got one of these. Lid blower. Okay. So when I go, we'll see if we can get it to start. I have to do a choke. Let's go with a choke. Probably just wrote every morning health and safety handbook for running engines indoors and all that kind of stuff, but I thought it was funny, so we just did it anyway. But the reason that this is how it works is that the reason that ball bobs around in the airflow is because when the air hits the ball is a curved surface, and air sticks to a curved surface. This is something called the Coanda effect. I'll stop the microphone. Okay, sorry. And when air flows over a curved surface, it sticks to the curve. And so if you imagine the ball is in the airflow, if it tries to move that way, it pulls the air with it. So if you pull on the air that way, what does it do? What does the air do on the ball? Pulls it back. So any direction the ball tries to move, it gets pulled back into the airflow. Now with an aeroplane wing, when it's flying along, the air hits the surface of the upper part of the wing, and it's pulled down onto the top surface of the wing. And that pulling of the air down onto the top surface of the wing causes the air to pull the wing back up, so it generates lift from the top surface of the wing as well as the bottom surface of the wing. And that's actually how the wing works. And if anyone tells you things about the new illusions and things, you're welcome to learn all that. but the description I've just given you is absolutely correct, and you can never be faulted for that explanation of how we work. Now, what should we do next? Shall we talk about why things float? Because I've shown you that what happens when we make things cold, they shrink and sink. So now let's consider a different example. Let's make things a bit hotter. Now I'm standing behind this grill, you can probably see me through it. What we've got here is a turntable, and on that turntable is a jam jar lid. And I've got in this bottle some hexane, which is lighter fluid, effectively. And what we're going to do is start a fire here. We're going to make hot air rise, and I'm going to put this grill around it, and I'm going to spin it. So the air, which is going in through the grill, is going to be turning. And as it goes from the outside towards the middle, it's going to be turning in a smaller circle, obviously. So what that should do is, for reasons of conservation of angular momentum, it should make the air speed up. Now I can do a demonstration to show you this. We're going to need a volunteer. Hands up. Hands up if that's a volunteer. So, yes, that gentleman there. Brilliant. Yes, you come down. Fantastic. Thank you. Are you good at ballet dancing? Good, excellent. Come down then. What we're going to do is show you how a hurricane works. And believe it or not, the same science that underpins what a ballet dancer does when they do a pirouette, that's what you're going to be doing. What's your name? Carla, that's exactly what you're going to be doing. And when an ice skater spins on the ice, that's exactly the same as why a hurricane works. So first of all, let's actually demonstrate this, and then I'll explain the relevance. So, Jacinta actually is a pretty good dancer, so she's going to show you what you've got to do, and then you're going to attempt to replicate this. So you might have to go over there, because there's a little bit more space. So, when a ballet dancer does a pirouette, what they're doing is distributing their mass over the biggest possible area. They're spreading all their mass out and turning. Now, if you turn your mass in a very big circle, it has a lot of momentum. In a circle, that's called angular momentum. When they want to go fast, what they'll do is pull all of that mass in towards the centre of rotation, the middle of their body. And because all that mass is no longer turning in a big circle, it's now turning in a small circle, it can't go with less momentum. So the only way for it to have the same momentum is to speed up, which is why they go very fast when they pull their mass in. So we should be able to demonstrate that with your help. So can you demonstrate this for us, please, Jacinta? Not bad, right? Do you want to go? Go on, there we go. Have a go. Do your best. Oh, beautiful. Let me show you actually a sort of different take on this. Okay, I'm going to have a go at spreading my mass over the biggest area possible. I'm going to start slowly. Okay. And I'm going to speed up, and in a second I'm going to pull all my mass into the centre, and I should go faster. You see it? I'm really easy now, so I'm going to go a little bit. But that's actually what's happening. Now, what's the relevance to a hurricane? Well, with a hurricane, where do hurricanes fall? Over the Gulf of Mexico. Where's that? Near America. Very good. Good in geography. Excellent. You know more about geography than most Americans do. So the Gulf of Mexico gets a lot of sunshine for a long period of time, and it warms the water up. The water evaporates. Yes, we're nice keep moving too. Great. The water evaporates and warms the air above the water. So you get this rising column of hot, low-density air. So if the air is rising, what comes in to replace it? Cold air. Where's the cold air come from? Further across the planet's surface. What's the planet doing? Turning in a big circle. So if the air coming in is turning in a big circle, and then we move the air into a small circle, what must happen to its speed? Speed up. And that's why the wind speeds in a hurricane are very, very fast, close to the eye wall of the hurricane. And we should be able to demonstrate this with this experiment. Could you do the lighting for me? It's over here, I think, isn't it? Oh no. Yeah. Sorry, because my Hansen went out, I lost it. Right. Just put this in here. And we might have to have a couple of goes at getting the grill on, because it's a bit tricky. So we'll just move that to there. Do you want to light that up for us? Yeah. I'm going to have to go at getting the grill to stick down, because it's a slightly tight fit. I'm getting there, everybody. Sorry about this. It's just slightly tight to get this to plug on. Okay. Can you turn the lights off? If we just turn this round, what you see is a flame tornado. And if I let it stop, it goes back to normal. If I spin it the other way. And what you're seeing is the air accelerating as it goes towards the centre and turning a faster and faster spiral, which is why the flame gets into a very tight column. And actually we call that flame tornado. Pretty cool, huh? So that's the same reason that hurricane works. Bring the lights on. Now, what else floats in the air? Who can suggest some things that float? Who's been up in a hot air balloon? They float in the air, don't they? How does one of those work? Right, we could try and make one, couldn't we? What's this I've got here? A very high-tech piece of apparatus, this, very expensive. That's called a bin bag. What's in it? Yeah, there's air in there. How much does that weigh? It's not that big.
10 grams.
Well, this has got about 60 litres of air in it. And believe it or not, air weighs about 1 gram per litre. So how much does the air here weigh? 60 grams. Now, I showed you that when I cooled down the helium balloon, it shrank. So I took energy away from the gas and it shrank. So if I give energy back to a gas, what does it do? It gets bigger. So if I heat up the air in this bag, what will happen to it? It will expand. Will it all fit? So some will fall out. So if it falls out, what will happen to the mass, the weight of the bag in the air? It will drop. So this bag doesn't feel like it weighs anything because it's floating on the air in the room. It's pushing out of the way an amount of air that weighs the same as it does, so it doesn't feel like it weighs anything. If it pushes out of the way more air than it weighs itself, what will happen to the bag?
No.
Must go up in the air. So what we've got here, in this box, I have borrowed Jacinta's toaster. You can see that in there. And that's going to be my supply of hot air. I've got this cardboard box on top because the cardboard box is going to keep the bag away from the toaster because otherwise it will make bag toast. That won't taste too good for Jacinta to have a breakfast tomorrow. So we're now filling the bag with hot air. The air is expanding and it'll probably expand by about 10%. So it'll lose about 6 grams of mass. And the bag only weighs about 4 grams. So we should end up with something with a net upward force of about 2 grams. Here we go. You can legitimately describe as rubbish. Now, there are other gases helium. What's lighter than helium? Hydrogen. Hydrogen is the most abundant element in the universe, and in fact about 90% of what came out of the Big Bang War was hydrogen. And I've got a big cylinder of it here, on the floor. And I'm going to connect that cylinder to this apparatus here. This is a shower head underneath a solution of bubble bath. So I'm going to blow bubbles of hydrogen through bubble bath. Turn the valve on. Now normally when you blow bubbles, they've got air in them. So as a result, they're full of air, which weighs the same as the air in the room, and they sink. Whereas these bubbles, full of hydrogen, are going to be very, very buoyant. And we should be able to make a big tower or snake full of these bubbles. So if I take this off of here and do that, you see, they do that. So it should be possible to make a very big tower of these bubbles. That's what I'm going to try and do. What's the other property of hydrogen apart from being very buoyant? It's quite flammable, isn't it? So the problem is that once I do this, you know, I've got a big column of this. We can do sort of snake charming with this. It's like belly dancing, but with hydrogen. I'll just turn that off for a second. What I've actually now got, unfortunately, is better described as a bomb. So Jacinta, could you get rid of this for me? Light it, light it, light it. And then bring it up gently. Go. Pretty cool, right? There's really nice smell of burning hair over here. Is it yours? Should we do it again? Should we go for a big one? Really big one. Really, really big one. I was in South Africa about a year ago, and people really got into the let's do it, let's go large, like Burger King. And they kept saying, bigger, bigger, bigger. So we ended up with this thing that was sort of twice the size of my head, and the bottom was really quite impressive. Here we go, 3, 2, 1. That's actually quite a small pop because the hydrogen in the bubbles is not at very high pressure. Because the bubbles are quite weak and the gas can't expand very much before the bubble will pop. So the reaction is quite limited. Can anyone tell me what the reaction is that we're seeing there? Hydrogen, H2, plus oxygen, O2, goes to water, H2O. We need to balance the equation, don't we? So how do we balance the equation? 2H2 plus 1O2 goes to 2 molecules of water, and a lot of heat. Yeah. But not as much heat as we could get out because there's not much hydrogen there. So how do we make the reaction more powerful? More hydrogen. I like that, man. There you go. There you go. I'm looking for my safety goggles, but I can't find them. These ones. There they are. So what I've got here are some balloons, and they're full of hydrogen. And this is, of course, hydrogen under quite considerable pressure. So the volume of hydrogen to go off is now very big. So if we light this, we should get quite a big pop. Shall we have a go? Yes. All right then. Jacinta, do you want to light your candle? It's here. I might do away with these here, there's things in here. Right, okay. Are we ready? Okay, do you want to count us down then? 3, 2, 1. There's a bit more hydrogen in here. Here you go, here you go. the hydrogen is all in the balloon. We told you it's reacting with oxygen, O2, and where's that? It's in the room. So the two can't actually get together until the reaction starts. And so it takes time for the two to mix, it takes time for the two to react, and all the time the heat and energy from the reaction is escaping. So how can we make the reaction go faster? Well, we could mix the hydrogen and oxygen together in the balloon, couldn't we? Which would be extremely dangerous, because then you have all of the reagents you need in one place for that reaction to happen, and happen extremely fast. Which is exactly why we're going to try and do it. In fact, what we're going to do is to mix the oxygen and hydrogen together in the right ratio, so there's twice as much hydrogen as oxygen, so all of the reaction should happen in an instant. Now when you do this, because all of the reagents are there together, and they're going to go off all at once, what it will do is release so much energy so quickly that the air will be superheated around the balloon. And this will make the air try to expand around the balloon, and the air will try to expand faster than the air can get out of the way. What's that called? That's called mental. It's called a shockwave. This is how thunder works. So if we got this right, we should get quite a big pop. Okay, shall we have a go? Okay, people in the front row want to put the kids in here. I'm going to be outside. Right, are you ready? 3, 2, 1. This time, I have made the mixture a little bit better. So it's as close as we can get it to 2 to 1. So it should be the perfect reaction mix. So you really should hear this if you didn't hear it before. Are you ready? Okay, here we go. 3, 2, 1. That's fantastic, the way you keep people up. But it isn't necessarily the best use of hydrogen and oxygen. There is a more practical use. Can anyone tell me what it is? Well, actually, this is the same science that gets rockets into space. And I'm going to show you how that works. I've got my own rocket here made of a lemonade bottle. And we've put about half the bottle is hydrogen. I'm going to take the lid off and I'm going to let the water flow out of the bottle into this bucket so that the air is going to go in and replace the water, and we'll end up with a mixture of hydrogen and oxygen in the bottle. And I'm going to put the bottle into this rocket launcher and we're going to light it. And what should happen is that the reaction will go up inside the bottle, the hydrogen will burn in the oxygen, produce lots and lots of hot gas which will expand, and the only way out of the bottle is out of the back end. And if the bottle pushes loads of gas out the back end, the gas must push back on the bottle and push it along. So show how we go. Okay, put the bottle in the launcher, and I'll just get out of the way, and then Jacinta can... 3, 2, 1... Yeah, it's very, very hot. You see the steam coming out. The hot things expand. That's why that works. Have you had enough yet? No. Well, we got home now. No. Do you want some more? Yes. Okay. Well, I've got another experiment here. I was in South Africa, as I said, and I thought I'll do an experiment that will be relevant to South Africa. It's very important to appeal to the locals when you're doing something like this on their country. And so I thought I'll make a bomb. Because I thought, what's South Africa famous for? Who can tell me? Gold mining. Yeah, they do a lot of blasting. But let's show them how that works. So I stood up in a situation like this and said to the audience, what's South Africa famous for? And they all shouted out corruption. Whoops. So anyway, we're going to show you how a bomb works. I'm going to need some liquid nitrogen. Get my So when you make something blow up, actually the way it works, let's get some of that in there, bring that over here. When something blows up, what's actually happening is that the thing that's exploding, the fuel, takes up very little space, and then when it explodes, it usually turns from a liquid or a gas into, liquid or a solid into a gas. Gases take up about 1,000 times more space than the solid does, or the liquid does. So if they take up 1,000 times more space and there isn't room for them, what must happen? The thing they're in must fall apart, mustn't it? Which is exactly what happens when you drill a hole in rock and you pack an explosive into the rock. The rock can't get 1,000 times bigger, so it has to break. Now our bomb is going to be this Sprite bottle. Let's take the cap off that. Just a minute. Got my earphones on. This is just in case it goes wrong. Pop those on there. Right. Now I've got idea what I'm saying to you, so if I talk gibberish, I apologise for that. Right, let's take this liquid nitrogen and I'm going to pour it into the bottle. There it goes. So pouring the liquid nitrogen in there. Very nice. So I've probably got about a fifth of the bottle. I might put a little tiny bit more in. Let's take a bit more of that. Okay. Tiny bit more. Now that's completely safe, isn't it? Because what's happening to the gas when it turns into a gas from the liquid? Where's it going? Coming out the top. Yeah. So I have to put the lid on there. No. What happens if I actually screw this lid up?
Let's blow.
Now what's happening to the pressure in the bottle? It's getting really high, isn't it? So what's going to happen to the bottle? Is all this stuff going to fit? No, it's not. So we'll just drop this in here. Put that there. And we'll go over here. You keep an eye on that. Pretty catastrophic, isn't it? Would you like to see what's left of the bottle? Not very much. So you can probably appreciate how a devastating explosive actually works. Had enough now? No. Want some more? Yeah. So that is actually the end. I have got one more thing I can show you though. Okay? Alright then. We're going to get one go at this though, so I have to get this right. Not that I had enough go at that, but I'd been dead if it had gone wrong anyway, it wouldn't matter, would it? While the guys rig this up, because we need to get these bits and pieces together, we have to, I need you to say some thank yous for me. Okay? And I'll just tell you what's going to happen. So, we'll say some thank yous to some very fine people who helped us to do all this, and then we'll try this final experiment And when we've done the 5 experiments, if we're still alive afterwards, there'll be an opportunity for anyone who wants to ask any questions, and anyone who's sick and tired of us by then can go home. The only thing I would say is it might make a mess, and I'm sorry guys, if you haven't had a bath today, you might want to move this aside a bit. But please don't come down into what happens down here, because there's all sharp bits and things, we don't want anyone to get hurt. It's slippery. I don't want anyone to fall over. So please go to that side over there and want to talk to us, and we'll come and say hello to you afterwards, okay? What I'm going to do in this bucket is a large amount of very hot water, and there is a bubble bath in there, okay? And it's got a whole bottle of bubble bath dissolved in this water. I'm just mixing that up. There. And over here, I've got a very large amount of liquid nitrogen in this bucket. Just doing my coat up, because the last time I did this, it all went up my trouser leg. Here we go. Get my trousers on here. Right. Now, I told you that when the liquid goes from a liquid into a gas, it gets about 1,000 times bigger. Can you move that forward a tiny bit, please, Jacinta? So if I've got about 5 litres of liquid nitrogen in here. So if I put 5 litres of liquid nitrogen into a bucket of very hot water, the hot water will give energy to the liquid nitrogen very fast, and in under a second it should turn the liquid into a gas, which means we should be able to make about 5 cubic metres of gas in under a second under a whole bottle of bubble bath. And it could get messy. I'll give it a go. Before I do it, can you please say a very big thank you to the Australian Embassy and to the British Embassy who have made all this possible. Thank you. Thank you very much. To Jacinta who brought this whole thing up and thank you to my wife and Sarah and Tim and Amelia, my children down here. Their first time in Croatia as well, so they come to tell me if I'm doing a good job or not. Anyway, thank you guys very much. Shall we do it? Yeah! Thank you, you've been a wonderful audience. I've had great fun doing this. I hope we'll come and do it again. But in the meantime, have a lovely evening, what's left of it, and I hope we'll see you on the other side. 3, 2, 1, good night!
So I